Okay, should I start the presentation now? Okay, I guess I'll begin the presentation. So for my final, can you guys hear me just before I continue? Just put a thumbs up or say something if
Yep.
you guys can hear me. Okay, great. So for my presentation, I'm going to be covering a paper called Deep Leakage from Gradients. It's in a theme of security for ML and in an area of private machine learning. So increasingly, modern ML and AI applications are extremely distributed and require cooperation from many different scientific, medical institutions, or industry institutions that don't necessarily want the data that they're training their neural nets on to be given away. Many tasks are collaborative, such as you can think of training patient data. You would not want any data on, for instance, people's demographics, people's health to get out, because that would be a violation of the law and people's privacy in general. So the question that is to ask, is it safe just to share data or just to, yeah, is it safe to just share data or without encrypting it? Just put it on a model and send it off. But you don't send off the data, you just send off the model that's pre-trained. You wouldn't think that there's actually any kind of data that's retained within the model because it's just weights, it's just numbers, it's just reacted and trained on that data. So that's what the threat model that we're looking at for gradient leakage. People give some gradients and weights, they train a model. So for instance, on patient data, maybe perhaps recognizing a type of cancer or recognizing a type of cell or anything of the like. They train each individual, trains a bit of their data on it, and sends off the gradients or weights to a bigger code base for some other people to train their gradients and weights and recontribute to the code base to continue training the model. However, this threat model assumes that there can be a malicious entity trying to grab those gradients or weights to try to steal data or compromise the privacy of the entire model. So we're looking at an algorithm called deep leakage from gradients, and this is a little bit of pseudocode for how that kind of works. It's kind of like doing a backwards training to try to figure out what's going on with particular inputs. So at first, you'll give a model, you'll give weights, and you'll give some gradients to this algorithm. You generate some random dummy data in the same dimensions as the type of data that you train the model with. And then after that, you'll train a model with this dummy data. You take the gradient, and then you compute some type of loss function, in this case, MSE, over the gradients and the dummy gradients that you just produce. Then you do a back propagation with some optimizer, and you continue this iteration over and over. And until you eventually return that dummy data, and hopefully it looks a lot like the original data. So the implementation motivation for this is first to figure out, does this even work? Is it straightforward to implement? And then furthermore, while looking at the paper, there was a lack of discussion on optimizers. So using Atom, SVG, or using any other kind of optimizer, can it make this process more efficient? So in a way, this was an extension to the paper. This is an example of just using the MNIST dataset, running just a 5 through. After a few iterations of doing this algorithm, I could perfectly reconstruct a 5 that was inputted. This was some of the data just from testing. So as we can see, by increasing the batch size of training the model, the performance does go down on reconstruction, but some optimizers actually fare better. And this was actually not discussed in the paper. So we can see Atom is actually pretty resilient. And for some reason, it performs even better at a larger batch size in some cases. Additionally, I tested this with different hidden layers. So for instance, we can see that LBFGS is really resilient to increasing the amount of layers. However, SGD seems to fail, and it doesn't seem to be that good on the task for the limited data set that we used. So additionally, some findings where DLG is really quick and it's not a resource intensive process. And in the small studies, optimizers seem to greatly affect the rate of reconstruction. Additionally, different optimizers appear to be suited for different tasks, but model complexity and batch size seems to destroy the reconstruction. Thank you. That's this paper did use some data from deep leakage from gradients, and it was mostly original code. However, some was changed from, I used some of the author's original work in this. So any questions?
Yeah, so my first question sort of has to do with what kind of model you used, and second, if there were different models that you tested. I'm asking this because in your pseudocode, you seem to have like a generic sort of model that you use. And is there like any sort of effect? Like, let's say you use ResNet versus some other kind of model. Like, is there any effect on the reconstruction?
Yeah, there's an effect. So in the original paper, they tested against ResNet and a few other models. However, for generalizability, I wanted to make sure that I was using a similar type of model while testing different parameters. So I only use fully connected linear models.
Right. So, was there any mention in the original paper about using like ResNet? Because I'd imagine because ResNet's output, as we all know, is like input plus the output, right? Because there's like a bunch of skip connections and like whatnot.
Yeah.
So I imagine that reconstructing stuff for ResNet and stuff that has like um skip connections would be hard in this case. But I don't know, I'm just thinking about it, I guess. Was there any mention of that?
Yeah, they actually went over Resident 18 and they used it for up to about 5 layers, and it was pretty successful. And I used some of their code and I played around their code tweaking just the amount of layers on ResNet, and it seemed pretty effective. I can't remember the exact point at which it started to break and exactly what parameters started to break at, but it seemed pretty effective for ResNet. But for this paper, it was just a bit easier to run the experiments using fully connected layers.
Yeah, for sure. I guess another related question is I'm just asking all my discussant questions, I guess. Um, Sort of another related question is MNIST is like it's just black and white images, right? So essentially you just have like a matrix of like black and white or grayscale values. And generally, if you extend stuff to like colored images, things become like a bit harder. So did you try this on colored images as like just like out of curiosity?
Yeah, I tried on color images. So the original code did use color images and it worked pretty well. However, when using color images for this, sometimes it would work, sometimes it wouldn't work. And but I if I use exactly their code, it did work. So there might have been a few things in their code. Um, it might have been a few things in their code that would allow them to more successfully reconstruct images in full color. So
Yeah,
for instance,
and
one of the things they
oh,
used, they
sorry.
mentioned their paper was one-hot encoding. Oh wait, is it time for the next presenter?
Oh, no, 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 no. It's you started a bit early, so
Yeah.
we still have a bit of time.
Okay. So as I'm saying, one of the things they used in their paper was actually one-hot encoding, whereas I wanted to see as well if you could just put a model in without doing one-hot encoding and see if you could actually reconstruct it. And it seemed pretty successful in this black and white data. One of the things I would definitely like to figure out is what's the threshold for, data complexity before reconstruction becomes really difficult. So, like you said, with colors, how many dimensions, how much complexity in data actually causes to break, and how much of a case by case basis is that?
Yeah, and that's all the questions I had. I'm guessing we're supposed to wrap up right now.
Yeah, they said 3 minute discussion. Is it time for the next presenter or anyone
Uh,
can ask now?
I don't know actually.
Is there
Uh,
a TA?
but yeah. Mm, I think they did say it was time for us to like wrap up.
Okay,
The next thing starts at 3:41. So yeah.
3:41. Okay, cool. I'll just wrap up now. Does anyone else have questions from the chat? I guess not. Okay.
Oh, I guess I had another question. Just out of pure curiosity, you initialize the dummy data, right, with
Yeah.
just random stuff. But let's say you kind of knew that you were working with numbers, right, in the case of MNIST. So is it theoretically possible you'd get like a better reconstruction? Let's say you initialized with something that looked like the image of a digit, and then you just ran this process, and you got back like a dummy data. Is there anything like, is it like in initialization dependent, or is it just like
So
um
they didn't say anything about it, but this is a learning process at the end of the day. I'm pretty sure if you got something kind of close to it, it would be easier. But that's just there's no guarantee on that because I haven't done it. But to me, because it's a learning task and you give it something a bit close to what it's supposed to reconstruct, I think it wouldn't have that much of a hard time making the jump.
for sure, probably like it would just converge to it faster or something of the sort.
Maybe. Or it could
Cool.
also like start it on a path of wrong convergence. So for instance, you give it a weird looking one or a really different looking one, and then those features are not similar to the features that actually has extract.
Yeah, that's fair.
Okay,
Yeah, thanks.
thank you. I think it's time for next presenter in a minute.
Hello. Hello. Can you view my screen?
We can hear you and view your screen.
Okay. So I'll be speaking on solving the credit assignment problem without a backward pass. So what is the credit assignment problem? It's the estimation of how much each parameter must be updated to decrease the error in the output. And till now, the most popular method is the backpropagation. So backpropagation is used in all the state-of-the-art tasks in complex cognitive problems. The algorithm is basically the calculus chain rule, and based on the network error, there is a change in synaptic trend that is updated. So what is the issue with backpropagation in terms of biological plausibility? So first is the weight transfer problems. The weights for both the forward and the backward computation has to be symmetric, that is the transverse. And then we have non-local information used for updates, that is the global error is propagated, and all the errors are propagated through downstream weights. And the frozen activity during error propagation and the parameter updates, that is the separate forward and backward computation is performed. And then the update locking problem. So basically the backward computation has to be complete before the next forward pass. And in our brains, we say that the neurons are never stopping. It's never stagnant. It's always active. So the frozen activity, update locking, and the non-local and the weight transport problems are genuine problems. So what are the prior works done in this area? We know the backpropagation already. Then we have the feedback alignment. For feedback alignment ensures that we don't need the weight symmetry. We don't need the exact transport of weights for this. We can have random matrices B2 and B1 and use that to update our weights. And then we have the direct feedback alignments where we can project this error in terms of B2 and B1 and use it to parallelly update all the weights all together. Hence the weight symmetry as well as the frozen activity is reduced here. DRTP is the target projection. What we use is not the top-down approach, that is the global error is not used. Instead, we sample the error from the input samples itself and then use it to update the individual errors. Here in our work, we will be showing the forward-only algorithms. The forward-only algorithm consists of the Pepita and the forward-forward. What the Pepita stands for is present the error to perturb the input to modulate activity. What it does is it generates an error based on one standard forward pass and uses this error and projects it into the projection matrix F, which is constant, and then uses it to modulate the inputs and then again performs another forward pass, which is the modulated forward pass. And based on this modulated and the clean pass, the weights are updated. Second is the forward proposed by Geoffrey Hunter in 2022. What it does is the input sample corruption. The positive samples are the standard clean samples, and the negative samples are generated using masking, that is correct label with corrupted input image, or the correct image with a corrupted label, and then uses it to, for the positive samples, the goodness of the layer, like each hidden layer parameter is increased, and for negative samples, the goodness of each layer is decreased. The goodness is shown through the P equals to sigma of the good HL, the sum of squared neural activities minus theta, that is the threshold. So what are the results for the forward? As we can see, with increasing neural network depth, we have the different test errors, as we can see from the graph. So the average test error is for a 3-layer network is 0.49 for CFAR 10. And for the backpropagation test error, it's 0.425, which is very close to the forward. We also see the test error for MNIST is 0.17, and from the graph we see that the test error for MNIST is around 0.08. That means that the FF test error is lower. And we also have the effect of batching. The batching is not shown in the original paper, but we have tried it in our experiments. The batching means the goodness evaluated for a many number of input samples and then updating based on the collected goodness. And we see that if we have a small batch of around 5,000 samples, the error reduces from 0.42 to 0.07. So what are the issues with forward? So the method of updating, as we can see here, is the collection of the sum of squared neural activities, and then we have the logistic function depending upon a threshold. And then we have the loss combination of positive and negative samples. The update rule makes it difficult to converge towards the global minima due to it being unsymmetric. So what we try to do is to make it more symmetric. Also, with increasing number of layers, the error tends to increase. So the symmetric loss function, what it does is just take the difference between positive and negative goodnesses, and then the loss function is updated with this custom loss, and where we can see that the benefits, the test error reduces. And these are the results using the Pepita. So what we have is that for 2-layer NN, the accuracies and the BPs are very close, as long as the 3 layers and as well 4 layers. This also has the issues that with increasing layer sizes, the accuracy tends to diverge from the backpropagation accuracies. And we have the test accuracies for MNIST as well, which is very close because those are simple tasks. However, the issues are the feedback matrix is randomly initialized and not updated. So what we can use is a weight mirroring technique, which actually updates the feedback matrices as well as the forward weights, and which is better aligned with the transports of the forward weights, and hence with the update, the accuracy improves by 2%. So our takeaways are, all these algorithms are in the infancy of development. So it follows bioplausibility as well as it is energy efficient, and till now it works only for shallow fully connected networks, and there are further scope of developing it in convolutional as well as different learning rules. So questions?
Yeah, so I had a question about like how you trained your model. So like how many epochs did you run, and like do you think like if you trained it longer, would it help your forward or not really compared to like back propagation?
Yes, definitely. So the number of epochs required for forward is definitely more than the back propagation for now. It is because the back propagation is more vectorized learning. Each update is concentrated towards each of the nodes, whereas this has more variance. To control the variance, it requires more epochs or more number of neurons in a hidden layer. So in that case, yeah, the number of epochs, if it increases, it betters the test error until the capacity of the network is over.
Okay, yeah. And um kind I guess like out of the two, like Pepita and the forward, like what do you think would be more successful? Because I see like the Pepita had that got like worse, I guess, in accuracy as it went on. It's like what you
Yes.
think is like
Yeah.
better?
Yeah, so the Pepita alone has worse accuracy as it moves on with the increasing number of layers. But with the weight mirroring, if we also update the feedbacks, then the accuracy increases. As well as in currently, what we are doing is if we normalize the activity, like the hidden layer activities, as well as if we weight normalize, then we can further increase the neural network depth to 6 to 7 layers. So this is also in the work which is in development right now. And yeah, people are examining it differently. Yeah.
Yeah, that's all my questions because the next person has to present. But thank you.
Thank you so much.
Hi, can you guys hear me?
Yeah.
Okay. And can you see my screen?
Yeah, we can see.
Thank you. All right, so hello everyone, my name is Subha. Today I will present my project, which is a semi-supervised framework for MRI volume segmentation. So segmentation is an important pre-processing tool for a variety of applications. This is widely used in medical image analysis. Manual segmentation is costly, takes a lot of time, and suffers from intra and inter-operator variability. On the other hand, deep learning-based automatic segmentation methods rely on data. Usually, the more labeled data there is, the better the performance. So both of these problems can be solved by semi-supervised learning, which leverages unlabeled data to improve the performance of a deep learning model. Now, previous research has employed different techniques in semi-supervised medical image segmentation, such as consistency learning, pseudo-labeling, or some form of correction learning. However, these methods do not take into account the effect of cognitive bias within the model. The paper that I chose to reimplement and extend focuses on this particular issue, and it does so by employing a mutual correction framework. My motivation for choosing this project is to analyze advanced semi-supervised segmentation models, which can help answer subsequent research questions, such as MRI volume classification. So this is the process of the mutual correction framework proposed by the paper that I studied. This architecture uses both the labeled and unlabeled data, and it has two networks, subnet A and subnet B. In a nutshell, the idea is that if a volume passes through the two subnets and they give different predictions, one of them has to be wrong. So those are the predictions that need to be corrected. They've used a contrastive difference review module to find out these inconsistencies and perform a review training. There is also a dynamic competitive pseudo-label generation module that determines which of the two subnets is performing better at a given time. So, and then it dynamically selects that as the generator of pseudo-labels. So that means that these, the roles of the two subnetworks are not fixed. Rather, they can vary during training. So in my work, I have focused on improving the two subnetworks to improve segmentation performance. So in the paper, VNet is taken to be subnet A. In subnet B, the encoder of the VNet is replaced with a 3D convolutional ResNet 34, which is termed 3D Res VNet. In my extension phase, I have modified both the subnet A and subnet B in 3 ways. So first of all, I've employed a multipath encoder model in the networks. The reasoning behind this is that MRI volumes include structural features at different scales. So my hypothesis was that a smaller encoder path with larger kernels would be able to retain the large scale information from the input. The outputs of the two encoder paths are added and then sent to the decoder. And like the first encoder path, skip connections go from this new one to the decoder as well. The next change was in the skip connections themselves. Instead of using a simple skip connection, I have included an identity block in the model. This is done to extract richer features from the encoder side and directly propagate them to the decoder side. And since this identity block also includes a skip connection, in the worst case scenario, this will just learn the identity mapping from the input to the output. So the performance will not get compromised. And finally, taking inspiration from the attention unit architecture, I have employed attention gates before the skip connections merge to the decoder side of the network. This is done to emphasize the relevant features of the skip connections and to suppress the irrelevant ones. For the attention modules, the output from the layer before acts as the gating or the query signal. So these are the results from my project. The table shows output from different variations of the model that I've tried. The top row is the model from the paper MCF. The bottom row is my final model with all the improvements. So this shows that all the models yield satisfactory performance in segmenting the left atrium from MRI volumes. Looking at the last two rows, we can see that the edge-sensitive 95 HD and ASD matrices improve after adding the attention module. So this suggests that the attention modules might be helpful in improving edge segmentation accuracy and thereby reduce bias. However, the difference in performance between all the different models is very slight. So this questions the validity of the assumptions that I had before. So overall, I think a possible explanation why the modified models didn't perform significantly better is that I have not tuned the models to have the best results. So all the versions use the same default hyperparameters, which were the ones that produced the best results for the original MCF. The modified networks might be under-optimized in this case, in my opinion. So here we can see visually 5 consecutive slices from a random test volume. My takeaway from implementing the project is that analyzing mispredictions can improve the performance of a deep learning model by reducing bias. Unlabeled data can be leveraged effectively to increase segmentation performance, which can be very powerful. And finally, my main takeaway is that to improve a model, a thorough evaluation is needed in which all the components should be optimized, because otherwise we cannot accurately judge whether our hypotheses were valid or not. So this was an overview of my project. Thank you very much for listening. Is there any questions?
Yes, I have several questions. My first question is it supervised learning or unsupervised learning? I got kind of confused there.
Okay, so it's not supervised learning, and it's neither supervised or unsupervised learning. It's falls somewhere in the middle, actually. So in this kind of in semi-supervised learning, what we basically do is we use both labeled and unlabeled data. So the idea is that even though we don't have the actual ground truth for some data, we can still use them. We can use them to find the inherent structure of the data and use that information to improve our performance. So that performance can be segmentation or classification or something else, but it falls somewhere in the middle.
Okay. Another question is then if it's a semi-supervised learning, then how the data distribution looked like? Was there like labeled data and unlabeled data mixed up?
Yeah, do you mean in my project?
Yeah.
Oh, okay. So yeah, so in the project, I have actually not explained it, but so in the training phase, I have used 80 volumes, and in the testing phase, there were 20 volumes. So out of the 80 volumes in training, there were 16 of them were labeled, and the other 64 were unlabeled. Well, actually, I should clear it up a little bit. It's not that they were unlabeled. I still had the labels, but for the purpose of this study, we just did not use those labels. So we treated those data as if they don't have their ground truth labels. So we just treated them as unlabeled data.
Okay. So can you explain the result visualization part where as far as I remember, I've seen some segmented pictures, I guess.
Yeah, so
no,
I
not
did
that. Yes,
this
this
one.
one.
Okay,
Yeah.
So I kind of skipped through it. So the top one is the image of a left atrium. These are slices of a random MRI volume, random test volume, so 5 consecutive slices. The middle row is the ground truth, and the final row is the predicted volume. So these are the predictions from my model, my improved model. And you can see that it's just qualitatively speaking, it is pretty good. There are perhaps some differences at around the corners or the edges. That's actually the problem region. Most of the bias come through these, but qualitatively speaking, this is pretty good.
Yeah. Okay. About the architecture part, I didn't actually fully understood the architecture. Can you please elaborate the main architecture?
Oh, okay. Yeah.
This one. Yeah, this one. Yeah.
Okay, so I'll just go through it really quickly. So basically, we have our input volumes, and we have both labeled data and unlabeled data. And we have two different networks, and they're named subnet A and subnet B. And so the labeled data goes through these two networks, and so does the unlabeled data too. And so during the label data, you can see that the two subnetworks are actually outputting like different predictions. And so we analyze these differences, and then we find a difference label. So we know that this is where, I mean, there's a mistake here. One of these networks has to be wrong. So this part is, this information is used. And in the unlabeled data, so the subnetworks will output some kind of a label, like a segmented volume. But which one of these two volumes should we use? So it really depends on, at the moment, which subnet is performing better. So whatever this, whichever subnet is performing better, we take that subnet's prediction to be the pseudo label, and that and there's an unsupervised loss that is added in all the losses. So I actually sort of rushed through it, but the next presenter should begin now. So I will stop presenting now. Thank you very much for listening.
Can you see my screen and hear me?
Yeah.
Yeah, okay, thank you. Hi everyone, I'm Farhan. I'm going to present my project on Edge Enhanced 3-stage deep network for image super resolution. So what is single image super resolution? On a surface level, it means creating high resolution images from low resolution input image. For example, if you have an image of 64 into 64 pixels, the super resolution task is to interpolate the image to higher pixels such as 1024 into 1024. The problem is, however, severely ill-posed, as you have more pixels to resolve with less number of measurements. Historically, interpolation techniques have been used in super resolution tasks. However, with the advent of deep learning, convolutional neural networks are also employed for single image super resolution. Convolution blocks are also used to reconstruct the missing pixels in a data-driven approach. However, the convolutional operator causes a blurry effect, which we will see later in this presentation. Recently, residual channel attention blocks have been found useful in single image super resolution tasks. The idea of channel attention blocks is to use subsequent attention layers instead of convolutional neural network, which in turn retains the high frequency information in the images. In this work, I have re-implemented a paper titled Two-Stage Network for Single Image Super Resolution that was published in CVPR 2021. In the first stage, the input low resolution image is converted to a low resolution image with high frequency information. Consequently, in the second stage, the low resolution image is converted to a high resolution image with high frequency information. In addition to that, I have extended the work with a Sobel operator based neural network that retains the edge information and reduces the over smoothing effect of the convolutional neural network. In the original paper, there are already two loss functions. I have added another loss function for edge enhancement. The building block of the original two-stage network is residual channel attention blocks. As we can see, there are several residual channel attention blocks, shortly RCAB, and each residual channel attention groups, shortly RCAG, consists of 15 RCABs. So the input image is passed through several RCAGs and an upscale module to convert the low resolution image to a high resolution image. In the second stage, the target high resolution image is converted to a low resolution image with high frequency information. After passing through 8 RCAG and a downscale module, which is basically a max pool operation. And we can see from the loss function, the primary loss is between the predicted high resolution image and the target high resolution image, and the second term loss function comes from the second stage network, where the loss is calculated between the predicted low resolution image with high frequency information and the low resolution image found from the first stage. As an extension, I have incorporated a third stage where the input LR image is passed through a Sobel kernel Sobel kernel has always been used for extracting edges from images. That's what motivated me to incorporate the Sobel kernel for extracting edges. As we can see from the network, the input is passed through several kernel and the edge image is passed through several convolutional block as well as one upscale module so that we get the high resolution image at the end. The target image is also converted to an edge image and another loss function is calculated for edge enhancement. So to validate my approach, I used 800 training images and 100 test images. So the first image is the prediction of a simple convolutional neural network based super resolution, and we can definitely see some blurring effects. However, the prediction of the twisted network is much sharper. To fully understand the efficacy of the proposed edge enhancer block, we need to analyze the difference images. As we can see the second figure, the edges are resolved better than the twisted network. So some things I have highlighted that I have learned during this project. So a trick that I came across is to load your full dataset in the GPU at once and then call the batches randomly in each epoch. That way I have reduced my training time significantly. I was able to train 4,000 epochs in 30 minutes, whereas previously 50 epoch took 3 hours approximately. So here are some references I used in this slide. Thank you, everyone. If you have any questions, feel free to ask me.
Hi. So you mentioned that you have 3 components to your loss function. There were 2 before, and then you added a new one. So did you are these 3 components weighted? Did you assign any weights to them?
Yes. So the first 2 losses were from the original paper. So in their paper, they have one way. They have 2 weights. The first loss is weighted with the value 5, and the second loss was weighted with 1. In the loss I have added as an extension, I used 0.1 as a weight.
So, okay, so how did you decide on this value? Because 0.1 is lower than the other 2. So is there a particular reason why you added less weight
Yeah,
to it?
actually I have performed some experiments to fixate on that value. So one trend I have noticed that if I increase the weight of the edge enhancement block as a loss, the output image, I have seen like sharper edges in the output image, but the other pixels were severely distorted.
So
That's
this
why I
was
used
an
lower values in the,
experimental.
yeah.
Oh, okay. Can you go back like one slide to slide 5, I think? Yeah. So you said that you converted a low resolution to low resolution with high frequency. I didn't really understand that. What is that exactly?
Yeah, okay, I think I can explain it from here. So as you can see, the low resolution image is passed through several residual channel attention groups, and we get this FHF. So this is a low resolution image, but as you can see from the second stage, that the high resolution image is passed through several RCAG and a downscale module, and we get LR prime. So LR prime is the image with high frequency information, but it's a low resolution image, and a loss is calculated between these two. So the high frequency information is retained through this loss function. So that's why we get a low resolution image with high frequency information.
Okay, so you're getting this high frequency information to basically from the high resolution image. So that would be,
Yeah.
I think, the original image.
Yes.
That was a high resolution. Okay, I
Yeah.
understand that. Do we have time for another question? Because I just wanted to ask really quickly. That is, you said that you're preloading data on GPU. How does that work? Because don't we in PyTorch, we load the data on every epoch, batch by batch. Yeah. Yes.
So what I did is
you have this dual loop setting where in first loop you load the data, and in the second loop you calculate the gradient. So what I did is I used a separate loop to load the whole data to the GPU, and in the in general epoch loop, I just called one of the random batches using a random number and just calculated the gradient. That's why the training time reduced like 50%.
Oh, okay. I understand that. Thank you. That's cool.
Yeah.
Thank
Okay.
you.
I think the next presenter should begin. Thank you, everyone.
Sorry. Can you guys hear me now? Hello?
Hi, yeah, we can hear you.
Okay, sorry. I was sharing my screen. So hi everyone, I'm Zhao Yu, and today I'm going to present my implementation of the paper accompanied of the 2020s. So the convolutional network used to be the backbone for computer vision. However, for more recent models such as Bayesian transformer and swing transformer, they borrow ideas from transformers such as the multi-headed self-addition mechanism to build models for transformer models for computer vision tasks. But as we know, originally the transformers are built for natural language processing. So basically, to make it work well with images, the swing transformer, for example, have to reintroduce some of the ideas from traditional CNNs. So now the question is, if the properties in traditional CNNs are still desired, then what are the potential left in them? And basically, to answer this question, the paper accompanied of the 2020s proposed a roadmap to modernize a pure CNN model to achieve the state-of-art performance. So this is the roadmap proposed by the paper. They start with a ResNet model, ResNet 50, and then through these 5 stages of modernization, they come up with this ComNext model, and my implementation follows the same roadmap. So the first step is the changes on the macro design, and which includes the changes on state ratio and the state layer. So basically, when we say state ratio, it refers to the ratio of the basic building blocks. So for example, in the original ResNet 50, that ratio will be 3, 4, 6, 3. And in this paper, it changes to 3, 3, 9, 3. So in terms of ratios, that will be 1, 1, 3, 1. And I think they do this because the swing transformer share the same ratio, 1, 1, 3, 1. And the stain layer is normally the first several layer of the model that is responsible for aggressively downsampling the image. And here in their ComNext, they replace original stain layer with this 4x4 convolution with strata of 4. I think in terms of downsampling, they did the same job. But in terms of computation, this is lighter. So in the second step, the paper borrowed ideas from the ResNext model to use a depth-wise convolution. So with depth-wise convolution, we can actually mix the spatial and channel dimensions separately. So for example, we can use a 1-by-1 convolution to just do the inter-channel communication. And then we can use depth-wise convolution to basically mix or analyze the information within the channel. And this is a property also shared by the swing transformer. Paper explores the idea of inverted bottleneck. So in the original ResNet block, they first use a 1-by-1 convolution to reduce the number of channels. So that the middle 3x3 computationally heavy middle layer can do less computation. But with the depth-wise convolution, since it already requires less computation, so instead of decreasing the number of channels, we can actually increase it. So we can capture like more patterns in the image, and thus we hope that the model is more capable. So in this step, the paper focuses on the effect of large convolutional kernel, and this is inspired by the vision transformer. The vision transformer, it's like non-local self-attention, give each of its layer like a global receptive field, which means that it can gather information from a larger region. So according to the formula here, so if we want to have a higher ERF, effective receptive field, we can choose to increase the number k, the kernel size, or the number of layers. But the error here. But since the error is under square root, so if we want to increase the ERF, so increasing k, the kernel size might be more effective. And they also use a trick here to move up the depth-wise convolution so that the middle layer is computationally heavy because they have like more channels. But if we separate the large kernel layer with the like the seek channel layers, and it will reduce the computation burden. This is the last step where they made some changes on the activation layers, so fewer activation layers, fewer normalization layers. They also have this introduce a separate downsampling layer just to do reduce the dimension and increase the channel size and between different stages. So that's the result from the original paper. They test the model on ImageNet, and that's the result from my implementation. I tested on Cyber-10. So as we can see, it's not strictly increasing. So for example, after in the last step, we reduce the number of activation layers and the normalization layers. As we can see, after applying that, there is like a almost 1% performance degrade, but we also see some promising result as well. So after we adopt the depth-wise convolution, for example, we see almost 1% increase in performance. And after we apply a larger kernel size from 3 to 7, we see another 1% performance increase here. And in my experiments, I first bring back the activation layers and batch normalization layers, and that's bring up the performance to 83%. And I further increase the kernel size from 7 to 13. And with some techniques from other paper, and that boosts the performance to 84%. So I guess the takeaway will be under strict condition, like testing or training conditions, like I only trained it for 9 epochs. Some techniques such as the less activation layers and normalization layers might not be as helpful as described in the paper. And some other techniques such as depth-wise convolution and large kernel might be more helpful on increasing the model's performance. And that's an overview of my term paper reference. And yeah, any questions?
Yeah, I have a question. This roadmap that you presented, how much does it depend on your application? What I mean is, if you have different applications, is it do you need to do different things, or is it more general?
Yeah, I think it's more general. I think this kind of updates on the architecture should apply to downstream tasks as well. Yeah, it should be very general. I think in the paper, they experiment on not just object detection, they also perform some other tasks. But in here, because I don't have enough time to do other like downstream tasks, so I only do the image classification.
Sure. And in general, besides like improving the results for that data set, what are the what kind of properties of properties do you get of this after using this modifying this ResNet convolutional neural net? What kind of properties that you get that you didn't have before?
Oh, you mean like how much improvement I have?
Yes, or I mean properties like in terms of I don't know, in training, how fast, or any other differences that you have now and you didn't have before.
Yeah, I think one properties we have is, first of all, let's do one by one. So the first thing is the ResNetify, right? So previously, we don't, in the original ResNet, they didn't use stepwise convolution. But with stepwise convolution, what we have here is the separation of spatial and channel mixing. And I think they use this property because this property is also shared with region transformer. I guess the basic idea of this paper is it borrows ideas from region transformers, swing transformers, and see if those ideas are applicable to the pure convolutional neural network. So here, they borrow the idea of separating the spatial and channel mixing with stepwise convolution. And here, so in the original ResNet, the number of channels are decreased for the middle layer, but here we can increase it. So that should give the increase the capacity of the model and make it more capable of identify different patterns in the image. And then another thing is this larger effective receptive field with large kernel. I think those are the properties that are missing from the original one. So the original ResNet is stacked like small 3x3 layers, but I think the point here is it might be more effective to use a large kernel size.
Okay, great. Thank you.
Was that the last presentation?
Yeah,
Yes,
I
it's-
think.
Okay, cool. I think I can stop recording then.